Good afternoon. I am very pleased and very honored to introduce Sir Mike Brady. So he is currently a professor and member of the Department of Oncology at the University of Oxford. It is maybe a second or third or fourth career, since Mike Brady recently retired as a professorship in information engineering. Professor Brady is the author of over 600 articles and 26 patents in computer vision, robotics, medical image analysis, and artificial intelligence. He is the author or editor of more than 10 books, and he was the founding editor of the International Journal of Robotics Research, which is considered now as the best journal in robotics in all the community, since it has the highest impact factor. Professor Mike Brady has been elected as Fellow of the Royal Society, Fellow of the Royal Academy of Engineering, Honorary Fellow of the Institution of Engineering and Technology, and Fellow of the Academy of Medical Science. Mike is also continuing a strong commitment to commercialization and success of science, and he has started 6 successful companies, and he is or has been a director of 7 others. Finally, Mike Brady was awarded the Whistle Medal, which is the UK's leading award for engineering innovation. I would say that more than his wonderful scientific achievement, Mike Brady is also well known and famous for his personality. I would say his love of life, his sense of humor, and finally, as a personal note, 2 things. When I was a young researcher, I attended several lectures by Mike Brady, and I will never forget them, and I will never forget Mike, and I'm sure that you will not forget Mike Brady's presentation. And last of the last, as a Briton people, I am particularly proud to introduce a Celtic cuisine from Scotland. Please, Professor Brady.
So I want to talk to you a little bit about a couple of things which appear to be very different, and then I want to bring them together at the end. But first, I couldn't come to a lecture here with Jean-Paul without mentioning the wonderful Georges Girault, who unfortunately couldn't be here today. Many of the people in this room will have been inspired and have known Georges for many years. I thought I'd give you a summary of my entire research career for the last 30 years. Fortunately, it fits on one slide. I was in the AI lab at MIT from 80 to 85, and I discovered one thing above everything, and that is the importance of wonderful PhD students. And in fact, ever since then, I've built my laboratories around PhD students, inspired by MIT. And amongst them were John Hollebach, Matt Mason, who is speaking at this meeting. Rod was a postdoc, but he was a graduate student at Stanford at the time. Tomas Lozano Perez, Eric Crimson. It was just a wonderful list of people. And then in 1985, I went to Oxford to start as Professor of Information Engineering. And in particular, I wanted to have, and I think it's a theme which Russ Taylor will come back to, I wanted to have something that was not just science and engineering, science and mathematics, but was a systems integration project. And we chose mobile robotics. But there is one thing that I've always believed profoundly in my life, and I recommend it to any young scientist, and that is that every 7 or 8 years you should reinvent yourself, you should relaunch yourself in a new direction. And so I started working, as I'll explain later, in medical image analysis, and in particular cancer, and in particular breast cancer. And then more recently, I've had a bunch of other reinventions into molecular imaging, and then retired, and now Professor of Oncological Imaging. So just to give you an idea what retirement means, so I am currently co-director of the Oxford Cancer Imaging Centre, and I'm deputy chairman of a company called Oxford Instruments. I've also got 3 of my own companies going at the moment, and a bunch of others that I'm involved with, and I'm going to talk about these 3 today, for a reason I'll come on to a little later. One other final thing, along the lines of this morning, and in particular that brilliant lecture just before lunch by Coato, I just thought I'd tell you one of my own personal drivers. I have to tell you that publishing papers and books has been fun, it's been satisfying, but nothing, absolutely nothing compared with watching doctors use my stuff in curing people. And I find that vastly more satisfying. So I've always wanted to have the results of our research used daily by thousands of people. Tomorrow you'll see a very similar idea from Rod. Now there's two things that fly from that. If you're going to have things used, thousands of people using things daily, there is a scientific consequence of that, which means that you have to address the fundamental problems that underlie those practical problems. And the reason is that systems are typically used by non-experts, and systems have to work 24/7, 99.9% of the time. And the only way they'll do that is if they're rooted in fundamental science. And there's a second thing, which is that universities don't, and they should not, build systems within quality processes. They don't sell systems and they don't maintain systems. And what that means is if you're going to realize this goal, what you have to do is you either have to license technology to companies or you have to start companies. And that's why I, together with several other people at this colloquium, have wanted to see our companies, wanted to start new companies. So mobile robotics was my initial driver, and here's a typical example of robot-guided vehicles in industry to date. You see these things all follow lines which you can see very dimly in the floor. And that's okay, but it's very, very inflexible. And so in the 1980s, Caterpillar, together with a company at the time, was a British technology company called GEC, made a system that could follow paths, and it was completely software programmed, and it used, as you can see, it was able to run between well laid down paths outside or inside factories. It had a spinning, rotating laser, and it basically retroreflected infrared laser off barcoded targets. That was the situation that was deployed in a number of factories at that point. And this is now, 20 odd years ago, 26 years ago. And the good news was that this robot always knew where it was. The bad news was it didn't know where anything else was. So if you walked between those yellow lines, you could become an industrial accident. In short, you could be creamed. I'm not sure how that translates, but you could be killed if you walked inside here and this vehicle came, because there's no way of seeing you. So we had a project which was collaboratively with GEC, which was to try to detect in real time obstacles and then take appropriate action to get around them, to avoid them, either to stop or to navigate past them. And there was good news and bad news about that project. The good news was we did it, as I'll show you. The bad news was that GEC sold its guided vehicle division to a perfidious French company by the name of CGE, who promptly killed the project. Now, I should tell you that the endpoint accuracy of this system was 2 centimeters, which might seem pretty good, but actually the comparison with wire-guided systems was 3 millimeters. So in order to compete, we had to get the accuracy of this system down to 3 millimeters. I should tell you now that we've got that down over a distance of 100 meters down to 0.5 millimeter. So the project goals that we had were to develop a real-time data fusion architecture. This is my young son. Develop a real-time data fusion architecture based on a growing set of sensors, some of which you can see ultrasound, you can see a laser ranger, there's a vision system on top. And we wanted to detect if a path was blocked, and if so, automatically replan an alternative, and ideally avoid collisions, for example, with people. And when I went to Oxford, having been at MIT, I was awarded a laboratory. And the laboratory, I just want you to know what a laboratory in the developing world was. This is something I have to tell you, which Her Majesty never ever worked in. This basement was a basement. It had no windows. It was accessed by a narrow stairs. We had to paint it ourselves, but it was ours. It reminds me of the first apartment that my wife and I bought. By the way, writing Oxford on the floor was not hubris. It was to provide points of interest on this otherwise matte floor for visual guidance, real-time visual guidance. So, the nominal trajectory here is a straight line, but the robot in real-time detects these obstacles and can slalom its way around them. Remember, this is 20 years ago now, and on really very, very weak hardware. If, on the other hand, you have an obstacle that prevents that slalom procedure, then it has to back off, and it has to figure out that in that situation it needs to make an alternative trajectory, plan a completely different trajectory, and it did so. And you'll see it run around in a second, and you'll see how small our lab was. So this is as it was 20 years ago, and this is a system that we took to the Royal Society to serve drinks. That guy was our funding agent. We didn't kill him. So basically, I said that we wanted to do this because we wanted this to be a systems architecture project, and we were very much influenced by a lot of the work that Rod Brooks was doing at the time at MIT, which was known as the subsumption architecture. And so we built a system which contained a huge number of processes, and I'll come on and say what they were in a second. So this whole thing was realized as a network of distributed processes. Just to make a point, that wasn't just because we were trying to do something that was fascinating in computer science. The idea of building this system was that the sensor suite that we had, the motors, the processors that had to be integrated in the system, continually increased both in number, the diversity, and the complexity. And so we needed something that could easily be augmented. Of course, the multiple processes in the case of vision also provide for parallelism, and therefore, and also by being redundant, for fault tolerance. So we could quite happily go and knock out several of these processes, and the system would still continue to work. And that's actually important for industrial deployment. So the way we built this thing was, at the time, was around a thing which we call a local intelligent control architecture, which essentially was a mixture of hardware and software. And that hardware was based around a thing which was called a transputer, which those of you who are of a certain age may remember. It was incredibly fast. It was 1 megahertz, and we had about 60 of these on our system. The whole thing would now run on a very trivial, so it just shows you the way in which computers have continued to advance over the last 20-odd years. And I mentioned these various things, so we had one part that was all to do with the development system, one part was to do with a stereo head, another to do with a mobile robot, and so forth. So there were whole interconnected systems to this. And this thing you keep on seeing, Lika, we licensed eventually to a little company called Guidance, and has now been deployed in, although with different hardware than the transputer, has now been deployed in over 5,000 systems around the world. And from those of you who have a software perspective, we ended up by building a very large, decentralized and distributed system. One of the bits I was interested in, I showed you in the video, was the idea that you wanted to get a robot to go on a nominal straight line trajectory. That was the planned trajectory, but the thing is that there were alternative actions that could be done, namely the slalom and the block path that I showed you. But then the question is, how do you deal with uncertainty in collision detection, given that you're dealing with noisy sensors, and how do you choose the optimal action, given that you've inevitably got imperfect state information? And the way I formulated that was to write it down as a kind of a Bayes expected loss, minimum loss problem, namely you try to estimate with sensors the state of the environment as to whether or not there's an obstacle and whether that gap there is passable. We have a prior probability distribution over those states of the environment. We have a number of decisions to be made, that's these up here. The There's a loss function, that's how much cost it is to make one of those. So this around here costs more than doing that, and that costs more than going on a straight line. And then we have noisy measurement data. And so we formulate the thing for those of you here at the Collège de France and who've got any minimal background in mathematics. This is a very straightforward Bayes minimum expected loss. And the way that's done is using those sensors on the vehicle. You try to figure out a pattern of whether or not there are obstacles on the left or the right or in front of you and so forth, and what the extent of those are as to whether they block the path. So that's really a project that I first did when I got to Oxford, and that was started 26 years ago, and it finished just on 20 years ago. And at that point, I had a fork in my life. And in fact, as a result of that, in 1994, I dedicated the rest of my academic research to cancer. Now, it's not obvious why you move from mobile robots to cancer, and the answer is the mother of my wife, who died with a breast tumor that was that size. And I started asking around radiologists in London and Oxford how on earth they could miss a cancer like that, to the point where by the time it was found, it had metastasized and she was inoperable and died. And I could not believe the answers I was getting, so I just quit. I just quit working on robotics, and I decided I would work in breast cancer. Okay? Now, as I'll come back to you later on and try to show you, actually the underlying science has got huge amounts of similarity. However, I have carried on doing some robotics research through a company that I formed in 1991, which is called Guidance. And so the next few slides, I'm going to talk to you about the work that we've done with Guidance. And then I'll come back and talk a little bit about cancer. So, as I said, GEC, the mobile robotics company, was acquired by basically, eventually part of Alstom. And so 3 of the former employees who'd worked with me on the project, led by a guy called Malcolm Roberts, and I formed a company called Guidance. And what we did was we developed a new scanner. This is one of them down here that replaces that laser scanner. And we incorporated our leaker technology, and we incorporated our obstacle avoidance methods. We very quickly achieved sub 2 millimeter accuracy, but we did that by better mechanical and optical design. And we did that over a range of 50 meters. And now, in fact, free-ranging navigation absolutely dominates factory automation. And our system now, we have this little company in England where we have about 100 people, has got 70% of the US market and has started to get through into Europe and Asia over the last couple of years. And we have an installed base of over 2,000 vehicles in factories all around the United States and Europe. Most recently, one of our biggest growth sectors has been in supplying mobile robots into hospitals. Now, originally, as you saw from that thing with the barcode, you needed to go and survey the, to pretty high accuracy, the environment. But then we don't do that anymore. We now learn, and we were inspired by a development in robotics, which was called SLAM, self-localization and mapping, which I'll come back to in a few minutes. And the reflector's now a single stripe with no barcode. And in fact, now we're doing non-target navigation. This is an example working in a big factory just outside Columbus in Ohio, which is part of an automobile component supplier. And this is dealing with paper rolls which have to be stacked 6 deep up to a height of around 30 meters. The systems that we ended up building based on these generations of scanners, I only show you this, not particularly I want to show you the hardware, except to say that what we do is we measured range and bearing to these targets. Range we estimate using phase shift, rather like a heterodyne technology. We use a particular filter, a Kalman filter, which is well known in robotics, which integrates the scanner data. And so we can get very, very rapid updates of pose. And then one of the big issues is how you deal with reject false targets. And for that, we use a very simple probabilistic method based on Mahalanobis distance. For those of you who know about modern robotics, our latest version, this is the board that's inside it, And what it does is it incorporates two things. One is a so-called particle filter, which relaxes the Gaussian assumptions, the Kalman filter, and it actually enables us to run SLAM algorithms within it. So that's actually done now in real time. So this is an example of the stuff that Guidance has produced. There are, as I said, there are over 2,000 of these things around. This is running around in at the moment, this particular clip in a rather empty factory. By the way, one thing that's rather unusual here is that the lights are on. In most factories, you turn the lights off. I mean, why would you pay the energy bill? You can do these things in the dark, and you'll get better signal to noise. The Port of Rotterdam, just to give you an idea, uses well over 100 AGVs for container stacking. And the point I wanted to make here is that there's been a continual flow, even though I stopped working in it. We've had a continual flow of science from Oxford to Guidance and back again in terms of new designs, both in terms of optical and radar, in terms of joint probabilistic distributed Kalman filters, particle filters, SLAM, and so forth. And my successor as Professor of Information Engineering is Paul Newman. So what I thought I'd do is I'd just detour briefly and show you a couple of the things that I think have been going on in mobile robotics research over the past 10 or 15 years, and which I think are actually pretty interesting. One of the most important, I think, has been this thing which is called simultaneous localization mapping. After all, if you walk around the Sorbonne, you walk around the 5th arrondissement, you'll very quickly figure out a map in your own head, and you don't need to go out and survey it, you know, like with telemetry and so forth. And that's the fundamental idea here, and the question is, how do you equip a mobile robot using only onboard sensors to build a map of its environment while simultaneously using that map to navigate around the environment? Mathematically, that requires real-time computation of the joint conditional prior, which is called the map, given a sequence of observations and some prior knowledge, which might be 0. Or it might be just a rough topological map. And initially, SLAM was developed and demonstrated for a robot equipped with a single sensor, single, not signal, working in a small room. So at MIT, with Woods Hole, John Leonard and Paul Newman, first of all, mapped 10 kilometers of the bottom of the Mediterranean Sea. That was by the late 1990s. Hugh Donald-White has built terrain maps, 10 kilometers on the side, using autonomous drone aircraft. Ian Reed and David Murray have extended SLAM into doing real-time visual control, building maps using vision for a large laboratory space. And more recently, there's been this notion of loop closure, which I thought I would just show you in case you hadn't seen it. So fundamentally, here's a robot that's commanded to go on a certain trajectory and to try and build a map of it. And of course, the further it goes, as errors accumulate because of slippage of the wheels, errors in the sensors and so forth, it gradually gets lost. And it keeps on taking photographs as it's going along. And there comes a certain point when it realizes that it's been here before. It sees the same view that it had seen before. That means that the end point of that trajectory has to be the same as the first point. And in order to do that, you can now do loop closure, because this point and that point, so any errors that have accumulated, you now redistribute over the entire trajectory. Okay? So that's done in a very simple iterative process to maximize the total integrated variance over the trajectory. And if you look at that and then you rebuild that map, then you probably can't see it, but there's a map in the center here that's in pink, and the black across is the two standard deviations of error. And if you put that thing down, you can compare it using Google Maps. You can overlay it onto Google Maps to find out where that was, and indeed it was traveling around the engineering triangle in Oxford. So that's known as loop closure, and requires that you recognize that you've been somewhere before. I'll come back and show you that in a second. As you're running around, there's been a lot of other ideas which have come around in the robotics research, again in mobile vehicles. One is removing assumptions of Gaussian distributions from tracking, which are known as particle filtering. Another one goes beyond that and starts doing dynamic adjustments of covariance computations, known as bundle adjustment. And then finally, you can extend SLAM to hierarchical representations of space. Let me just show you one example of that. Here's a data collection platform that Paul and a bunch of students have built in the lab in Oxford. And here's a car with a stereo rig coming down by New College and then driving through Oxford. And the moment it gets into the city centre, decides to break the speed limit. And then we'll drive, in this first case, 70 kilometres around Oxford. And it drives on a circular trajectory through a bunch of villages, stopping only for a couple of beers. And then finally repeats that trajectory. And now as it turns red, it's because it realizes it's seen that place before. So every time you see red, that's a loop closure like I just showed you, just running around a laboratory. And the bottom line there is that you can do 2,300 loop closures with no false positives. That's over 70 kilometers. Emboldened by that, they set off the vehicle on different days on a much larger trajectory over the whole of Oxfordshire in Britain. And again, as it turns to red, you start to, as it repeats trajectories, it'll increase numbers of loop closures. And again, over that 1,000 kilometers, it can map using 2,500, as near as damn it, loop closures with very few, and we'll build a map based around that in Oxford. But of course, you very quickly get to the point where you go beyond the reach of just doing precise metric. And in fact, if you want to drive from Oxford to London, it makes a great deal of sense to navigate around, have one scale for navigating around the centre of Oxford and another scale entirely for navigating around London. And so you can break the thing down hierarchically into a scale for the much smaller town of 100,000 people, which is Oxford, and the rather larger place, which is London. And again, Paul, by the way, has recently got a license to drive a robot vehicle with no driver on the Her Majesty's highways in the UK. The insurance industry are delighted. And just back to guidance, one of our more unexpected applications has been with Finnish National Opera to build systems that could move mobile scenery. And this is a company called Visual Act in Finland. And if you're wondering, that's the guided vehicle inside there. This is merely saying that even though we're working in industry, we've actually been doing quite a lot of basic science, including a number of things that have been published in journals like the IJRR, for example, using dynamic clotoids to fit trajectories for non-holonomic vehicles. But, you know, if you're in a company, you begin to ask the question, well, okay, you know, we're doing all right with mobile robots, but is there anything else that we can do with our navigational capabilities? And here's one. This is a supply vessel in the North Sea. This takes quite a lot of effort to get this photographed because the sea is calm. This ship has to hold position between 15 and 25 meters away from the rig. It must under no circumstance hit it, and it has to hold position while supplies are taken on and off the vehicle. That's known as dynamic positioning, and basically most ships now use, of course, either GPS or either the Russian, the Chinese versions of it, like GLONASS, Compass, and so forth. Though, even in the Northern Hemisphere, that's not sufficiently accurate, and so you have to do what is known as augmented GPS. But currently, dynamic positioning requires that you have 3 independent position measurement systems for certain maneuvers, where independent means that you have to have that refers to the failure mode. For example, you cannot have 3 GPS, because if one GPS will go down, all 3 likely to go down. And so what we've done is we've developed, based on the mobile robots, we've developed 2 additional sensors, one of which is based on laser, works over 250 meters, and one is a radar system that's been developed for dynamic positioning. And we currently have 60% of the laser market, and we have 30% of the radar market. And that's all based on this very simple little project that I showed you earlier from Oxford. So the laser sensor, just to give you an idea, looks at retro-reflecting targets on these offshore platforms, and it does it by using a range of reflecting targets and by doing automatic leveling, because remember that the sea is likely to be bouncing this thing along, and so it enables it to lock onto a target even in quite increased sea states. And we have to worry a great deal about the false target problem. So here's an example, couple of examples. This is, well, you can see it better on the next one actually. Here you can see the side scan laser sensor looking up at the target, which you can see quite clearly. Now this is a beautiful day. Well, by English standards, this is an absolutely stunningly beautiful day. However, the weather is quite often like that in the North Sea. And indeed, let me show you 3 photographs taken over 5 minutes in the Sea of Norway. 1, 2.5 minutes later, 2.5 minutes later. Right? And the sensors have to work absolutely. The insurance claim, if this ship hits that rig, you pay hundreds of thousands of pounds in damage. It has to be able to cope with a massively changing environment like that. And so what we've done is build a radar, a frequency modulated continuous wave radar, which has an accuracy of 0.5 meter up to 200 meters and works out to around 1 kilometer. And there's a bunch of other things in here. And what I wanted to draw your attention to, for those of you who have any idea of ever working in any practical thing, is this is not how to do health and safety. This is a bunch of guys being held on a crane to be hoisted off, to be dumped onto a ship when this ship arrives, and they'll get dropped onto it. This is how on earth, well, apart from BP, of course, in the Gulf of Mexico. And so again, you can see one of these sensors up at the top and one down the bottom. Now, I couldn't, since I was here, I wasn't sure what your background was. There are only 2 equations. There's only 2 equations, well, 3 in this talk entirely. I wanted to show you one because I want to make a point right at the end, and I can't make that point unless I show you a couple of equations. So basically, the way a frequency modulated continuous wave radar works is it outputs a bunch of coded signal pulses, and it repeats every 250 microseconds. So it just bangs out this pulse. And it gets a received signal, which, if you model the physics, is written down in that form. Now, that's simply a sinusoidally varying, temporally modulated signal. And every single one, most of the things in here are known. The only thing that's not known is that. And that time offset is what enables us, in the end, to compute the range. So by modeling the physics of the situation, we can get down to figuring out what that temporal offset is. And then there's a second step, because you then have to model, when you send out this radar, it may reflect off the sea. If the sea is rough, it'll be scattered all over the place. It may hit a target and come back and be scattered all over the place. So you have to be able to model the reflectance and polarization of sea state, whether it's glassy, choppy, rough, etc. And if you model that sea state, and how could you get that? Well, for example, by the amount that the ship is bouncing around, you can not only solve for bearing, but you can solve for normalized range to target. So the fundamental thing is, if you forget the equation, by modeling the physics of the situation, both in terms of the reflection and the sea state, you can get bearing and you can get range. We've deployed this on several hundred vehicles now. What? Like that? Oh, sorry. You know, it's amazing. This is the first time in my life everybody ever told me to speak louder. My wife usually does quite the contrary. Okay, I couldn't resist showing you this because here we are in Paris in the 5th arrondissement. So one day we've got all this navigation stuff, and a guy shows up to our company and he says, well, he says, you guys, you're pretty good at making mechatronic devices. Will you help us? So what he had in mind was the following, and I just want to show you, we started with mobile robots in a little, beaten down laboratory in Oxford. We formed a company. We have loads of examples of that. We then got doing navigation marine, and then this guy comes along. Well, it turns out here's some numbers from the UK to think about. 6% of offenders in the UK commit 60% of crimes. 4% of the targets of those crimes are involved in 40% of crimes. The prison population has increased dramatically since 1995. That's because we have had a succession of conservative governments, or in the case of Tony Blair, neo-conservative governments, who have believed that the only way you can deal with criminals is to bang them up and shove them in prison. In fact, the only reason that crime is slowing down in the UK is because the prisons are full. So they're building new prisons, and Australia is taken. There are now, one way to keep people out of jail is 17,000 people are now on tag. And right now there are 10,000 in France, although that number is set to treble over the next 2 years. And we got the contract to build the tags. And this is just a mechanical design. But actually, if you put this thing on somebody's ankle, then in essence it turns out it's the opti-fiber anti-tamper strap. The very simple point I want to make is that the optics that went into that were exactly the optics that went into that little laser scanner that we used in our lab in Oxford all those years ago. Strange how applications go. And this is a typical monitoring center. And this is part of London. It's actually very close to Buckingham Palace, which of course there are a whole family of criminals live. And this is Paris. You can see the Seine up here. By the way, I may not be able to return to the UK after this talk. Well, that's okay. So, meanwhile, back at the University of Oxford, I became fascinated by cancer. I don't know how many people are around this room, let's say 150. On the average, 50 of you will get cancer at some point in your life. That is just a statistical fact. And that percentage is increasing. We do know that the earlier you diagnose cancer and the better therapy regime means that you've got much better prognosis. So, for example, what killed my mother-in-law when she had something that size, we can now detect while it's a size smaller than my little finger. And the woman has a chance now of 98% of having that cancer detected and treated. That's not true for prostate, it's not true for stomach, it's not true for a bunch of other cancers. Okay, so some successes, namely the breast, but huge number of challenges. For example, pancreas. If you get pancreatic cancer, you have a chance of 1 in 50 of surviving 2 years. Okay, I want to concentrate on 2 points. I only make 2 points in this talk. So here are a number of facts. 11% of Western women will develop breast cancer. And the earlier the diagnosis, the better the prognosis. And so that's why there are screening programs. So there are 3 million mammograms per year in the UK, and nearly 60 million worldwide. But 1/4 of cancers are missed by radiologists. Okay? And that's not because they're dumb, it's because these are bloody tough images. That's about as easy as they get. You can see extensive microcalcifications here. You can see a spiculated mass just in there. Here you can see another mass, but you can see how it might actually have been occluded by normal tissue. So the point I wanted to make with that first equation is now made on the couple of slides after this. Here are 2 mammograms. And you can see one was read by a radiologist called BK, one was read by a radiologist called TLS. And what they were trying to do was to estimate the amount of dense tissue, which is shown light here, which is in particular the percentage of dense tissue, because that's a key risk for breast cancer. The one on the left estimated 25%, the one on the right estimated 40%. And that's unfortunate because these mammograms were taken 10 minutes apart and it's the same woman. Now, we shouldn't be surprised by that. After all, if you remember photographs where you could change the film speed and the f-stop and so forth, you could get very, very different photographic appearances. So the point is that image intensity relates to anatomy in a very complex way. which makes for any form of quantitative analysis hard. And so in the 1990s, I spent the entire 1990s modeling the passage of X-rays through breast tissue. And what we ended up with, coming up with a quantitative representation, which even though the intensity here is 3,401, doesn't matter what the intensities are, it turns out we can figure there's about 4.3 centimeters of dense tissue. Here, the intensity is half as much, but we still figure out there's 4.3 centimeters of dense tissue. And fundamentally what we're doing is we're taking this image, we're generating this quantitative representation where the z-axis now is in centimeters, and the way we do that is by modeling the physics, and that's exactly what I did for the radar. So you end up with the amount of so-called interest in tissue, since fat is of no clinical interest, except when you're extremely fat. So basically what you end up with is taking the passage of X-rays through the breast, and in essence, I don't want to go through this, but fundamentally by applying standard stuff to do with what is known as Bayes' law about the attenuation of X-rays, and knowing the separation of the plates, you can solve for that quantitative parameter I just showed you. And more recently, the problem with that is it requires a lot of calibration data, which is a problem well known to people in robotics. And so more recently, we've gone back with a guy named Martin Yaffe from Toronto and Nico Karsemeyer from Nijmegen, and we've realized that we can actually scale the whole thing by effectively automating the discovery of places that are pure fat. And what we've done is develop a system. First of all, we licensed our system to a company called R2 in the States, who have fielded several thousand computer-aided detection, here detecting a spiculated tumor, and then more recently for estimating breast density automatically. The woman on the right, who's age matched with the other three ladies, she has a 4 times greater risk of getting cancer than this lady does. So we've now processed this thing over 200,000 images. We gained FDA approval, which means we can sell it. And we're now, based on that physics that I just showed you, we've now got sales that are growing very rapidly indeed for estimating breast density in women. And that's beginning to take off in Europe now as well. Just one other thing. Here is contrast-enhanced MRI. And you probably see here this, what is in fact the right breast, just uniformly gets brighter. Here, if you look, there's a part there that looks as though it's getting brighter like a light bulb, and that's because that is in fact actually a quite large adenocarcinoma. And what you can do is by modeling the take-up over time of a contrast agent, you can detect whether something is malignant or not. And so you can begin to develop, in the very same spirit that I just showed you, you can develop some applied physics models of the take-up of contrast agent that get you into looking at whether something's cancerous or not cancerous. Just to show you an example, here on the left, here on the top is a conventional analysis that's used in hospitals around the world, where this is pre-chemotherapy and this is post-chemotherapy. The white stuff shows up as a tumor, and if you were given the pre and post images as a clinician, you would probably say, boy, this tumor is responding, we'll give it some more chemo for another 6 months. However, if you remap and try to interpret in a quantitative way what's going on here, you don't get that image, you get this image. And what you can see at the bottom is the necrotic center of the tumor, and around it you can see the advancing wave of proliferating cancer. And at the same point, you do it here, and you'll see that all the proliferating cancer's gone. Mrs. Jones, you are now completely cured. Mrs. Jones, you need 6 months more therapy. Right? Completely different. Absolutely, totally different. So again, this is now a product which we're selling. I'm going to show very quickly something, and I want to make one last point, and then I'm going to quit. For the last 9 years, I've been working mostly on molecular imaging. This is a very, very, very grossly simplified picture of a cell, and it's from a wonderful book by Robert Weinberg called The Biology of Cancer. And fundamentally, what it does is it looks at various signaling regimes around the cell. This is a most remarkable factory. And if you look at one of them, for example, one I've been looking at a great deal over the last few years is AKT signaling. And if you look at that in a little bit more detail, it talks about the proliferation of cells, it talks about the survival, so-called apoptosis of a cell, and so forth. And if you drop down from that as a mathematician, you end up by writing little flow diagrams of what's going on with inhibition and so forth. In fact, very much along the lines, and very much in the spirit, that Kawato-san was doing this morning when he was looking at the brain. We're modeling cellular processes for cancer. And we've been doing that, in essence, for a particularly resistant form of cancer known as hypoxia. And again, based on understanding the biology and the physics, we end up by writing down sets of coupled differential equations, which enable us to, we've been developing new targets for PET, which take into account the maths that we've done on these, and that's stuff that we've been publishing recently. And then finally, I just wanted to show you, when people are so-called cured of cancer, then in essence, increasingly what happens is you do some image analysis, which informs a therapeutic decision whether you have surgery, radiation therapy, or chemotherapy. Currently, about 49% of people have surgery, around 40% radiation, and around 11% chemotherapy. That number in surgery is reducing, and these two numbers are increasing, that one very rapidly, in terms of radiation therapy. And in terms of surgery, it'll either be conventional open surgery or more and more minimally invasive surgery, and I think Russ will probably talk a little bit about that later. In terms of radiation, it's either conventional X-ray radiation, or increasingly it's the use of proton beams, or indeed you can get high-intensity focused ultrasound, or indeed high-energy light in the form of photoablation. So just to make a couple of points, first and foremost, robotics is always based on sensor-guided actions, and every single one of these therapeutic options, every single one of them, more and more and more, is becoming closed loop. Right? More and more and more, the kinds of things you saw this morning from Paolo Dario, and you will see tomorrow, really begin to be applied to each of these various therapeutic options. So, for example, in the case of surgery, we've been looking in particular at what is known as endometriosis, which is a very, very nasty cancer. This is the nasty cancer here, which grows as a wall thickening between the bowel and the uterus and basically invades the uterus. And so a woman will get very, very painful cancer, which in fact can prevent her having children. And this is the bladder in here, just to orient you. And what you have to be able to do is to detect the thickening of the wall, the abnormal thickening of the wall, in this particular case of the bladder. And we've now got this running on a routine basis in Oxford in the clinic. And we're doing that for the bowel surgery using the Da Vinci robot that you saw in Jean-Paul's talk when he started out this morning. And this is a typical film footage of the use of the Da Vinci robot. More effort has gone into radiotherapy, and this also forms a bridge into what Russ will talk about. Namely, radiotherapy is advised if you've got small tumors, particularly, for example, in the breast or in soft tissue sarcomas, where you don't really want to have surgery because actually the act of surgery can spill cancerous cells and cause secondary cancers, or when you've got residual disease after resection. So you use this, for example, in the prostate or the vocal cord to clean things up a little bit after taking most of it out with surgery. But the prescribed dose is very much limited by adjacent tissues, you know, the kind of friendly fire collateral damage problem. And that's particularly true in the head and neck, in the lung, in the brain, and so forth. And the effectiveness of radiotherapy declines rapidly with increased tumor size. So I said you begin with images, and one of the things that's done nowadays in medical imaging is to combine an anatomically very precise imager, for example, computed tomography, which will show you basically a dense tissue contrast. You can see here the bones, and you can see some evidence of what might be a cancer in here because of the extra density of it radiologically. And PET, positron emission tomography, which enables you to image metabolism. And so the good news is this is accurate to around 0.1 millimeter, and this is accurate to around 3 to 5 millimeters. I mean, both of these are getting better, but that's directionally right. And one of the things then we want to be able to do is to take one of these images plus one of these images, and on the basis of that, in this particular case, one of those nasty hypoxic tumors, generate dose paintings. And because one image is very rarely enough, one of the companies I said I'd talk to you about, which is Marada, which is a company based in Oxford, but 1/3 of it in the United States, combines a CT and a PET and produces a fused image which combines those two information together. And then the idea is that you can identify tumors and you can track them over time, and if you do that, you can begin to produce, and this is one of the things we've done, we produce a picture of tissues, the various tissues labeled from an atlas, and the kinds of tissues to be avoided and tissues to be dosed. And again, this is something that Russ has done a lot of work on. So here you can see that this is carina, this is the spinal cord, this is the heart, and so forth, each of which have got kind of maximum allowable doses or recommended doses. So it becomes then a very complex optimization problem, which ends up by giving certain amounts of doses in terms of grey to those various tissues. Well, I'm aware I've covered a little bit of ground, and you may ask, what the hell do breast cancer, guided vehicles, marine dynamic positioning systems, and radiotherapy all have in common? And I put it to you that there are three things. First, every single one of them pose hard problems that are of practical importance. That's what I like working on. In both cases, whether it's marine or whether it's cancer, there is a danger posed to human life. Second, the signal and image analysis has to work almost all the time, and for that reason, it must be based on models. You can't do this thing in a heuristic way. And the kind of models I've tried to emphasize to you in this very, very brief talk are, first of all, of the interaction of X-rays with tissue, or radar signals with sea states, and with rain and with mist. You require that you deploy prior knowledge of the appearance, for example, of clinically significant signs, or indeed the anatomy that you expect to see in the head and neck. For example, the carotid artery, the throat, etc., the spinal column. And I've talked to you a little bit about cellular pathway models of cancer, which are becoming more and more the scientific basis of how we think about and how we treat cancer. Every single one of these, in the end, are based upon model-based signal and image analysis. Every single one of those is more and more becoming the basis for closed-loop control. I've always thought that robotics was the intelligence connection of sensing to action, and all I've done here today is talk to you about sensing. Thank you for your attention.